Hey guys, welcome back. In this video we are doing two more examples of distributed loads. So we have a constant distributed load here and also a triangular distributed load. And so let's see what we can do if we can solve for both of these. When we do solve for these, we need two pieces of information. We need the entire load that is being exerted on the object by the distributed load. And we also need to find out the location of the centroid of the shape of this distributed load because that will be important for us when we're solving for the moment that it's causing on the object about some point. So for the first one here, for a rectangular or a constant distributed load, it's pretty easy. We have 20 kilonewtons per meter, and this is acting on 6 meters. And so the whole load that this distributed load is applying is 20 times 6. That's going to be 120 kilonewtons. All right. The other thing that we need to do, as I said, we need the centroid, and because this is a rectangular, we know that the centroid is going to be right in the center of that rectangle, located halfway along the base. And so yeah, let's go ahead. Let's start our force balance here. We have the sum of forces in the y direction. Maybe we should actually draw on the reactions here too. So we have AY, and we'll have BY. And there's no horizontally applied forces, so we don't need to worry about the horizontal reaction at A. Alright, so the sum of forces in the y direction, we have AY plus BY is equal to, minus 120 kilonewtons. We can just say, bring it to the other side right away, is equal to 120 kilonewtons to get that force balance, because this object is in static equilibrium. And then what we want to do is we want to solve for the moments, the sum of moments about, let's say, A. We'll define on here a little positive sense. Alright, so the things that are going to cause moments about A is going to be this reaction here, and that was supposed to be called BY. BY will, the moment that BY causes will be the magnitude of that force times this distance, because it's perpendicular, so times 6 meters. And then the magnitude, and that was positive, right? Because that would give the tendency to rotate about point A in this direction, and that's what we're saying is a positive direction. Where you can see for the distributed load, it would give the tendency for this object to rotate the other way, and we're saying that's the negative direction. So what we're going to do is we'll subtract it. And in order to do this, the moment that's caused by this distributed load is the whole load itself is 120 kilonewtons. And the distance that we use is the distance from that point to the centroid here. And so that's 3 meters. That's 3 meters, and that was all equal to 0. So when we isolate for BY, we will get 120 kilonewtons times 3 meters all over 6 meters. And that's going to give us 60 kilonewtons. Okay, and when we plug that back into here, AY is equal to 120 minus 60, then obviously AY is also going to be equal to 60 kilonewtons. All right, and so there we go. That's all we need to do. The one thing that I should mention is right here where we did 20 times 6, there's kind of a graphical interpretation to this where if this rectangle, if we look at the shape as a rectangle with the dimensions of the base being 6 meters and the height being 20 kilonewtons per meter, then what we've really done, this is equal to just the base times the height of this shape. Now for a triangle, this gets pretty important because to find the total load exerted by this triangular load, what we're doing is here where we had base times height, we're just taking the area of this. So if we want to take the area of a triangle, it's going to be 1/2 times the base times the height. Now in this case, the base again is going to be 6 meters. So we have 1/2 times 6 meters times the height, which is 20 kilonewtons per meter. 20 kilonewtons per meter, then we're going to get a total of 6 divided by 2 is 3 times 20, and we cancel out the units. We're going to get 60 kilonewtons, and that is the entire force that is being exerted by this triangular distributed load. And if you also remember, when we were doing in the past videos, we had the location of the centroid For triangles, well, along the bottom it is 2/3 of the way away from the short side or 1/3 away from the tall side. So the centroid is going to be somewhere in here, where its x bar will actually be 4 meters. We're not too concerned about the height. We don't actually need it. We just need the distance away from A because we're going to be using the moment. We're going to be passing through this 60 kilonewtons, which is the total load, through that centroid to work our moment equation here. All right, so with all that said, I guess we can just, again, we can draw on our reaction forces here. So we have AY in this case, and we have BY. And the sum of forces in the y direction, we are going to have, again, we have AY and BY acting up. And then we have this 60 kilonewtons, so it's the total force from this applied, this distributed load acting downwards. So we'll just put that on the other side of the equation, and we'll have that's all equal to 60 kilonewtons. Now when we take the sum of moments about some point, we'll do the sum of moments, let's say about point A, and we'll define some positive sense here for our equation. We're going to have BY is going to be causing that positive moment, because of that it would have the tendency to rotate in that counterclockwise direction. So we have BY times the distance, which is 6 meters. And then the distributed load obviously would give the tendency to rotate this object like that around point A. And we have, so we can just bring it to the, well, we can just put it minus, or we can bring it to the other side of the equation if we want. Where we have the magnitude of that force, so 60 kilonewtons. And then times the distance to A was 4 meters here, so times 4. We can even write that times 4 meters. Alright, so if we bring this 6 meters down here, we'll get BY is equal to 60 kilonewtons times 4 meters divided by 6 meters. That's going to give us 40 kilonewtons. And that's the right units. We're looking for kilonewtons, and it's positive, so we know it's pointing up. Now if we just bring this back into this sum of forces in the y direction, we'll have AY is equal to 60 minus 40. So we're going to get AY is equal to 20 kilonewtons per, just 20 kilonewtons pointing up. So there we go. It's exactly the same process for a rectangular load as it is for a triangular load. You just have to find the total force exerted by the distributed load and then locate the centroid, because for the moment equation, that's where we kind of treat the resultant force, which is the total force passing through that point. And then you can solve for the reactions of the beam that we're considering.